Monir, are you able to see my screen?
Yes, ma'am.
Okay. So, do you have any doubt in the last class or in the last week, week third?
No, madam.
No. Did you attend the assignment?
नहीं मैडम, अभी बाकी है, आज करने वाला हूँ ऐसा है।
Okay. Can we start the class or we can wait for 2-3 minutes or for others to join?
Okay, ma'am. Wait for 5 minutes.
Okay. So did you attended the week 1 and week 2 lectures and week 3?
Yes, ma'am.
Okay. It's already 5 minutes about. We can start the class. Can we start the class?
Yes, ma'am.
Okay. Yeah, so in the week 3, we studied about the yield point phenomena and strain edging and different types of strengthening mechanism in aluminum alloys. So first we will start with the yield point phenomena. So what is yield point phenomena? Like if we apply stress on the component, this is stress and strain. So in aluminum alloys, there, as we know that there is a no sharp yield point. So after deformation, if we unload the material and reload after some time, then the yield strength will increase because of the uh, sorry because of the accumulation of solute atoms around the dislocation core, so that lead to the increase in stress required for further deformation. So this phenomena of increasing yield strength with aging, after means aging, if we keep the deformed sample at room temperature or left it for some time or for some days, then its strength will increase. That is called the yield point phenomena and strain aging. So it is also the time dependent process. If aging is only for a few hours, then there will be no difference in the yield strength after reloading. If it is for a few days or few months, if we say, then this increase in yield strength is observed. So this is the time and temperature dependent process. So how the time we can get the like for few hours, there is no significant effect on the stress, but for few months with increasing time the strain aging will increase. And the temperature effect on the yield strength is as the temperature, if the aging is at an elevated temperature, means above room temperature, so the solute atoms can easily diffuse to the dislocation core and pin them. Easily. So there is one Cottrell Wilby theory which is used to uh, explain the strain aging behavior in the aluminum alloys. So that says the one second. That says the in the around the dislocation. This is, if we say that this is core of the dislocation. So there is equipotential circles around the dislocation core. So this is tensile strain field of the dislocation, and below of the dislocation line there will also the equipotential lines. So this is compression field. So every potential line defines means describe the energy associated around that region. So the smallest circle or smallest line, so nearest equipotential line depicts the higher energy in the or the means higher energy dislocation around the highest energy dislocation field. So as the high energy distribution field, so and so the due to the difference at the strain field, like in this picture, due to the difference in energy of the strain energy, the solute atoms experience a drift velocity from the dislocation core, or so that can be away that can be away from the dislocation or near the dislocation. And again, what is happening are just wait. Okay. Yeah. Diagram is so due to the equation of the drift velocity is the v equals to d by kt, and this is strain field force applied. So k is the Boltzmann constant, t is temperature, and d is diffusion coefficient of the solute atoms. So the so there is an inverse relationship between the velocity and temperature. So if temperature is high, okay, the velocity will be low because the atomic coalescence of the solute atoms will be higher, or if there is no energy gradient, so there will be random jumps in the of the solute atoms because of its less applied energy. But due to the strain field gradient, the solute atoms occupy drift velocity and move to pin the dislocation as the dislocation move around during the deformation. What is happening? I will use the whiteboard. What is happening? Just wait. Are you able to see the screen?
Yes, ma'am.
Okay. Sorry for interruption. Yeah. So in the dislocation, there is the equipotential lines, and the strain energy gradient for each dislocation line is different. Means the nearest line has the highest energy, that the energy is strain energy. So due to the difference in strain energy of different equipotential lines, the solute atoms experience drift velocity that leads to attraction of solute atoms around the dislocation core. The equation of this is d by kt into F. This is applied force. So as the time, so in strain aging, as the time spent, the solute atoms diffuse to the dislocation core and pin them. That's why the after if the material is left unloaded after some point, the yield strength will increase to the higher stress. Means higher stress is required to uh, uh, mm, for further reformation. So next is the dynamic energy, dynamic strain aging. So dynamic strain aging happens in the substitutional solid solution alloys. Like for example, in aluminum alloys, aluminum magnesium is the substitutional. Means magnesium is the solute atom in aluminum matrix. So this happens because of the loading, unloading, and then reloading after aging. So high stress is that atoms are required. So this dynamic strain aging in the the difference between strain aging and dynamic strain aging is that strain aging uses the for strain aging we have to left the material for some few months, but the dynamic strain aging is during the deformation only. Like this is stress and strain. So the variation in the yield point and if this type of curve is fine. So this type of variation in the stress level with increasing deformation is called the serration. And the dynamic strain aging can also happen in the steels like plain carbon steel. So what is the effect of dynamic strain aging is that it decreases the ductility and toughness of the material. For example, in plain carbon steel, it happens around the 225 to 375 degrees Celsius in the range of this temperature. So in plain carbon steel, this is called blue brittleness. So the factors for dynamic strain aging is the dynamic strain aging, temperature and strain rate. So defining factors. Temperature and strain energy, strain rate. So only in the certain temperature and strain rate range the dynamic strain aging happens. So but this so this is called inhomogeneous flow in stress flow. The inhomogeneous deformation happens due to locking and unlocking of dislocation during the deformation process. The effect of dynamic strain aging is the poor surface finish, after deformation, that is known as the stretches strains. Strain marks. So in the dynamic strain aging, the deformation is localized in a band. So in the tensile test, if we see, sorry, so the so the deformation moves as the formation of bands, deformation bands. So the deformation can proceed as the increasing in the deformation, increasing the same deformation bond or nucleation of other deformation band along the tensile axis elongation. So the dynamic strain aging is localized deformation. The other name of dynamic strain aging is Poitevin PLC effect. Poitevin Le Chatelier effect. So other name of this is PLC effect. So in the strain aging, as we know that there is a relation between stress and strain rate. Like if we see, sigma is equal to K equals to epsilon dot power m. So sigma is the applied stress to deform the material, so it is directly proportional to the strain rate. If strain rate increases, the stress increases. Here K is the constant strengthening coefficient and m is the strain rate sensitivity. So with increase in sigma, with increase the applied stress increases with increase in strain rate. So during the due to the if strain rate is increases, the dislocation velocity also increases. Means dislocation movement will be higher, and in that case the solute atoms cannot easily pin the dislocation, the higher moving dislocation, and with increasing strain rate, dislocation can solute atoms find it difficult to catch the dislocation, and the waiting time of dislocation will decrease at the obstacles. So with increasing strain rate, this is the yield point, means the dislocation as the strain rate increases, the dislocation is free from the solute atoms, so that's why the stress decreases. Then after some time, if solute atoms are able to pin, then the stress will be high. So uh, this increase and decrease in the stress applied for the deformation is called the inhomogeneous, and that resulted into the serrated flow. So how this uh, time is related to the strain rate. So like if we say the strain rate can be written as the rho b v. So rho is the dislocation density, b is Berger vector, and v is the velocity. So for two locations, like in the material, if this is the distance L, so velocity will be rho b L by t. Here t is the waiting time of the dislocation plus flying time. So the flying time is very less than the waiting time of the dislocation. So in the equation can be written as the rho b L by t w. So waiting time, so if waiting time is less, that means strain rate is high. So for dislocation movement, the dislocation have to pass the activation barrier. So activation barrier has two components. First is the applied stress, and second is the thermal activation. So when there is no dynamic strain aging, the waiting time of the dislocation is very less, and the thermal activation provided for the dislocation is also less, because the time is all because the decrease in waiting time, the more stress has to be applied for dislocation to move. For dislocation as the it is. So the waiting time. So in the DS, so in this case is for the when there is no DSA. So stress increases with increasing strain. While in DSA, TW is as the waiting time decreases, stress to move dislocation will decrease also. Means when there is no DSA, there will be less effect of solute atoms. While in DSA, dynamic strain aging, the effect of solute atom pinning will be higher. So as the TW is less, the solute atoms cannot diffuse to the dislocation, and the pinning is less. So because of this, stress will decrease in the dynamic strain aging process. Like if we plot a diagram of stress strain curve, so this is for E1, and this is E2. So this is case for when there is no DSA. If DSA occurs, the stress for E2 will be lower than the E1. So E2 is greater than E1. Means if we see in consideration with the activation barrier, so activation barrier will be low when DSA happens. So this is for E2 and this is for E1 and this is for E2 when no DSA is there in the material. So according to the pinning theory, the sigma can be written as the sigma naught plus H E. Here E is the strain of the material and the sigma as a function of strain rate. So H is the strain hardening coefficient, and if this equation is differentiated with the time, so there is equation called like d sigma by dt. So that will be H, so d by dt will be strain rate plus d sigma, and then this can be written as this. So this term is the strain hardening. This is, and this is for strain rate hardening. So in a curve of stress strain, like if this phenomena is there, this is A, B. So this second term at A and B point, the slope of sigma and epsilon is this d sigma by d. D sigma epsilon by d strain is sigma naught 0 means, so the E double dot, if the differentiation of E dot is the E double dot, so E double dot is tends to infinite at A and B point. So when from A to B point, there is from A there is a shift in the strain rate, means the strain rate is changing from the A point. So if stress is applied, as the strain rate is changes from A, the stress decreases. So this is the shift in strain rate, because the highest stress is required. But because of the increase in strain rate, there is in DSA case, the stress will decrease to this B point. So if we take a C point around this, so with increasing stress, the deformation increases, and with change in the strain rate, if strain rate is increases, this will shift to this curve, then but the stress required is less, so it will go through the B point. But after coming at the B point, there is again the decrease in the shift in the strain rate, and because of the change in strain rate, it will shift to the point A. to this curve. And this process of decreasing and increasing stress with increase in strain rate resulted in the serrated flow like this. So this will continue with because of the inhomogeneous deformation and increasing and decreasing the strain rate because of the pinning of the dislocation with solute atoms. So this resulted in the inhomogeneous deformation and serrated flow. So the stress relationship with the strain rate is this. So if we want to find the strain rate sensitivity, we have to differentiate it in the log term. So m can be defined as the d of log sigma and d of log E naught. So strain the m is the strain rate sensitivity, and it is less than 0 in case of DSA, and strain rate sensitivity is positive when no DSA is there. The strain rate sensitivity is that with increasing its strain rate sigma will increase, and in the DSA case when strain rate is increases the applied stress will be lower. So what is the different features of serrated flow? So first is that DSA happens in a certain range of temperature and strain rate. Range of temperature and strain rate. So for a given strain rate, if temperature is increases, then the diffusivity of solute atoms will be higher, and they can pin easily. They can pin the dislocation easily, and stress will be higher. As the stress is applied, the dislocations are free, and then the stress will decrease. So the temperature range for aluminium alloys is room temperature to high temperature, and strain range is the 10 raised to power minus 5 to 10 raised to power minus 2 per second. So this is the strain rate and temperature range for aluminium alloys for dynamic strain aging to happen. And then the second, so for a given strain, the temperature is for then in the types of the second is the type of serrated flow. So in the type A, so there are three types of serrated flow. Like in type A, there is a step by step increase in the stress. So this increase in A describes that the deformation bands move continuously through the gauge length, and the humps and valley correspond to the disappearance of a band and initiation of a new band. In so second is the type A. B, there is a smooth transition of the or decrease and increase in stress level. And the type C is the sorry, for type A there is a continuous in progress of the deformation band, while for type B the because the humps and valley describe that the deformation first deformation band was stopped and the nucleation of new formation deformation band is there, means it is the disappearance and initiation of disappearance of old bands and initiation of new bands. While and in the type C rated flow there is a disrupted change in the stream. So this type of deformation resulted from the hopping of the band deformation band. From one position to another, means the one serration and one hope can be defined as the one. So one serration will form because of the one hopping of the deformation band. So the change in the deformation band types is the from A to B and C. So in the initiation of the deformation, first A type of serrated flow is found, then it changes to the B, then C type. If we plot the diagram of log of strain rate versus 1 by T, so between these lines the shifting in type of serrated flow is from, like, this point is A, this is B, and this is C. So out of these two lines there will be no DSA. So with increase in time, if temperature increases, the shift of deformation flow changes from A, B and C. So with increasing temperature, the changes in serrated flow follows this path A to B to C, and this point is C, and in this region there is DSA. So the serrated flow is always associated with the negative strain rate sensitivity. Flow means the negative strain rate sensitivity, means with increase in strain rate, stress decreases. So if we compare the dynamic strain aging in steel and aluminum alloys, in steel it is the diffusion of interstitial atom resulted in the dynamic strain aging, while for aluminum these are the substitutional atoms. So what can be interstitial atom like carbon and nitrogen atoms in the steel, while for substitutional atom there is magnesium in the aluminum. And there is also a critical strain defined for a serrated flow to occur. Like if we draw a sigma versus epsilon fire, so the serrated flow always happens after a certain strain. So this strain is called the critical strain. The effect of temperature is that with increase in temperature, the critical strain required for serration decreases. So this is the EC2. So this is T1 and T2. So T2 is greater than T1. So with increase in temperature, the thermal activation in activation barrier is high, and due to the thermal resistance, the solute atoms will solute atoms are easy to pin the grain boundaries. So the critical strain will decrease for higher temperature. So as the next point is that as a critical strain decreases with increase in strain rate, with decrease in strain rate, means that as the strain rate decreases, critical strain also decreases. For high strain rate, the critical strain is higher. So this also depend on the range of the strain rate. Like if we draw between critical strain and strain rate, for certain strain rate value, it follows the inverse behavior, but after some point the relation is directly proportional. So inverse behavior is only up to this point. And similarly, if we draw a graph between critical strain and temperature, there will also be a inverse behavior. So inverse behavior will occur in this. So with increasing temperature, the critical strain decrease. After some point, if temperature is very high, the critical strain is also increases. Because of the at higher temperature, there can be complex interaction between the solute atoms, dislocation and obstacles coming in the path of dislocation. next come is the magnitude of the serrated flow. So if we see the so the this is called the means there is a range of decreasing and increasing of stress with increasing strain. So this amplitude defined as the delta sigma increases with increasing temperature. So delta sigma increases with increasing temperature. So if then the plot is if we plot a diagram graph between delta sigma and temperature, so there is an increase in magnitude of the serrated flow, while if we plot a curve with delta sigma magnitude of the serrated flow and the strain rate, then there is inverse proportional between the so with increasing strain rate the delta sigma is decreases. So what is the effect of mechanical properties on the dynamic strain aging? So in carbon steel there is a decrease in ductility and toughness. Toughness decrease. While for aluminium alloy, the DSA results in the localization of deformation that resulted in the stretches strains, and the stretches strain marks uh, re- decrease the surface finish of the aluminium alloys. Sorry. Stretcher marks. So, well, so DSA depends on the vacancy concentration also. Dependence on vacancies. So, with increase in vacancies, if vacancy, so how vacancy resulted in dynamic strain in high increase in dynamic strain aging. Like if there is a decrease presence of vacancy, so diffusion of solute atom will increase. So as vacancies increases, the effect of dynamic strain aging will be higher. If lattice, if this so only vacancy are not responsible for the DSA. So the movement of vacancies in diffusion is resulted to lattice diffusion.
हेलो।
Yes.
मैम एक बार ये फिर से एक्सप्लेन करना है, क्योंकि मेरा नेटवर्क इश्यू था, तो इसलिए अगेन ज्वाइन करना पड़ा।
कहाँ से आपका छूटा है? ये मैंने ये
नहीं नहीं, ये यहाँ तक तो था, जो लास्ट आपने डिसलोकेशन वाला जो डिपेंडेंस वेरिएंस लिखा ना, वहाँ से
डिसलोकेशन वेरिएंस,
इसके
ये
नीचे नीचे
इंटरेक्शन।
सबसे लास्ट में, लास्ट वाला, सबसे लास्ट वाला।
अच्छा, ये वाला।
हाँ।
अच्छा, डायनेमिक स्ट्रेन एजिंग, हाँ, तो द डिपेंडेंस ऑफ वैकेंसी ऑन द डायनेमिक स्ट्रेन एजिंग इज दैट द डिफ्यूजन बिकॉज ऑफ द वैकेंसी इज कॉल्ड द लेटेस्ट डिफ्यूजन. But there is one more type of diffusion, that is pipe diffusion, that that occur along the dislocation core. This is along the this is the dislocation core. So the pipe diffusion along the line, so that will form as the pipe. So the region is called is looks like similar to a pipe, so that's why it's called the pipe diffusion. So the core can attract the solute atoms much more higher than the lattice diffusion. So the diffusion of solute atoms will be higher in this case along with the dislocation core, and the diffusion because of the lattice vacancies is less. So the main reason behind so the main contribution of diffusion is because of the dislocation core. Core diffusion is higher. So next is the force dislocation. That are different variables that depend, so that attributes to the dynamic strain aging. Like so, first is the lattice diffusion, second is pipe diffusion, and third is dislocation, porous dislocation. So as the dislocation moving through its active slip plane, so in the pipe, so the pipe diffusion only, the solute atoms will move to will drain from the porous dislocation to mobile dislocation because of this pipe diffusion. Means if there is a porous dislocation, means multiple dislocations are there, so from that porous dislocation region, the atoms diffuse need to this dislocation core, and means mobile dislocation, because the strain field of mobile dislocation will be higher, so that they can attract the solute atoms more. Like, and next is the cross core diffusion. Cross core means around the dislocation, the above is the tensile region, sorry, above is the compression region, and below the dislocation there is tensile region. So the diffusion of solute atoms also can happen uh, along the strain field of the dislocation, from compressive to tensile, or tensile to compressive. So what will be the case when compressive, then when the atom will diffuse from the compressive to tensile or tensile to region? If the size of solute atom is large, atom size is large. So in the compressive region it will create the more strain field, and so it will shift from the compressive to tensile. If solute atom size is low, then the shift of the solute atom will diffuse from the tensile region to compressive region. And in case of interstitial also, if atom size is higher, then it will diffuse from compressive to tensile, and if it is atom size is small, then it will diffuse from the tensile to compressive region. So so how can the dynamic strain aging can be prevented? DSL. So first method is the roller leveling or the temper rolling. In roller leveling, the sheet of aluminum alloy is fed to the roller, and it will deform like this back and forth. So that increases the deformation level of so that in roller leveling of small dia. So it is fed to the small dia rolls, and that resulted in the deformation that increases the dislocation concentration, and so the deformation will be higher and easy in the case of if it is pre-deformed. Roller leveling, and second is the temper rolling. So in the temper rolling, small reduction of the thickness is applied to the material. Small reduction up to 0.5 to 1.5% of the thickness. So as the deformation increases, dislocation density also increases. So with increase in dislocation density, more dislocations are present, and the solute atoms are less to bring the all dislocations. So the active dislocation are higher in number, because solute atoms are limited in the solute atom concentration is limited, and they can pin only certain dislocation. So remaining dislocation which are active can result in the deformation, and with maintaining the stress level. So there will be no increase in the stress because of the pinning of dislocation from these solute atoms. So the serrated flow can be avoided because of the roller leveling and temper rolling. Next is the avoid the strain rate and temperature range. So the strain rate and temperature range in which the inhomogeneous deformation occurs, we have to avoid that range. Next is the precipitation age hardening. Means strain aging and dynamic strain aging is over. So next is the precipitation age hardening. So precipitation happens in some few classes of aluminum series, like in 2x, in which aluminum copper is there, in 6x, aluminium, magnesium, silicon 7x and 8x. This is aluminium, zinc and aluminium, lithium. So the precipitation in aluminium copper is the CuAl2 phase. This is intermetallic phase. Then in 6x series, that is Mg2Si, and there is also precipitates in case of aluminium, zinc and aluminium, lithium alloys. So the precipitation of intermetallic compound with aging leads to the hardening and increase in the strength of the alloy. So how the strain hardened precipitation age hardening happens? So the criteria for the precipitation age hardening is the change in the solubility with increasing or decreasing temperature of the alloy. Means the solute solubility will be higher for at higher temperature. And it should decrease with decrease in temperature. With decrease in temperature. So if we see a phase diagram of aluminium copper, this is time, this is weight fraction of copper composition. So in the aluminium copper case, this is alpha aluminium plus liquid, or this is alpha solution. Alpha is the aluminium copper solid solution, and here it is the alpha aluminium plus CuAl2. So if we take a composition and heat it up to the single phase region at a higher temperature, means so there will be maximum solubility. This is the maximum solubility, and this line is called the solvers line. So from this solvers line, from this line we can see that with decrease in temperature, the solubility in aluminium decreases. So if we heat a alloy of composition up to the single phase region and quench it at higher cooling rate, so all solute are entrapped in the aluminium copper solid solution. Means the all copper is entrapped in the supercell in the quenched composition. So the quenched alloy is called the super saturated solid solution. Means the copper concentration is maximum in the super saturated solid solution. If this super saturated solid solution is left for some time, or means the time is around, can be days, months or years. So with increasing time, the increase in strength will be higher. So as the supersaturated is left at room temperature or high temperature, the extra copper atom diffused from the solid solution of alpha from alpha aluminium. This is solid solution which has the limited solubility of copper. So the copper extract out from the supersaturated solid solution and makes the intermetallic compound CuAl2. At higher temperature, the process of extraction of copper atoms from the supersaturated solid solution is higher because at higher temperature diffusion will be high. So the kinetics of the aging process will be high. So the treatment of heating this composition to single phase region is called the solutionizing treatment. Next is quenching and aging. So why only quenching is done to the solid solution single phase region? Because in the quenching high cooling rate will be provided that that entrap the copper atoms. Like if we see the time temperature transformation diagram, so here on the y-axis it is temperature and the on x-axis it is time. So a C-type curve is formed during the cooling of any liquid. So this is the single phase region temperature. So if cooling rate is high, so the first curve shows the starting of the starting of the nucleation of secondary phase, like 1%, and this is called the 100%. Means start and finish. So if cooling rate is low, then the curve will follow this path. So after the crossing this point, the precipitate will form, but it will be coarse, and the coarse precipitate is not required, because coarse precipitate will only precipitate out at the grain boundary region, that will lead to the intergranular fracture also further. Because in the low cooling rate, the heterogeneous nucleation can only happen at the grain boundary, and the homogeneous nucleation is low at the low cooling rate. So the copper is segregated to the grain boundary region, so that will lead to the formation of coarse precipitate around the grain boundaries and intergranular fracture. If the cooling rate is high, that it cannot cross the start and finish curve, so the copper solubility will be highest in the solid solution, and after aging of the solid supersaturated solid solution, fine precipitate will form. That is the nucleation of fine precipitate is also homogeneous around the grain boundaries and in grains. homogeneous precipitation all over the microstructure. So because of the fine precipitate formation and the also that precipitation is homogeneous, that's why quenching is preferred. Yes. So the lectures are over. Do you have any doubt in the to today's session?
No, ma'am. Thank you.
Okay. So can we discuss the different assignment? Just wait. So can we discuss the week 2 assignment? If you have not any problem, because week 3 assignment you did not attended yet.
यस मैम, वीक 3 का असाइनमेंट आज सबमिट करने वाला हूँ.
Okay.
Which of the following designation is normally wrote with copper? Second option, 2000 series.
Okay. Yeah. Copper is the major alloy. So second option is correct. Next question is the what does the second digit in wrought alloys designation indicate?
Second digit, major of element. Variation. Measure of yellowing element, second option.
No. Third is major
Okay,
alloying
ma'am.
element is the first digit. Means if we see the 2x, so first digit implies the major alloying element and the second digit implies the variation in the specific alloy composition.
Okay, ma'am.
Next question is what do 0 and 1 after decimal point indicate in the cast alloy designation?
Uh, uh, Ingot and finish casting respectively, first option.
No. Finished casting and 0 and 1 is the just wait. Just okay. Finished casting, the correct answer is finished casting and ingot casting. So 0
Okay,
is
ma'am.
used for casting, like if we see the 2x point 0, so this is used for casting only.
Okay.
So next is the which of the following aluminum alloys heat treatable?
2000 series, 6000 and 7000.
Okay. Next question is which of the following statement is correct in case of aluminum alloys designated as element 7 X.
Major yellowing element is zinc, first option. स्लाइट इज नॉट विजिबल मैम अभी 5th नंबर का ये जो क्वेश्चन वही आ रहे हैं
हाँ हाँ, वही पूछ रही हूँ मैं। इसमें ये मल्टीपल सिलेक्ट क्वेश्चन है, मीन्स
मल्टीपल
मोर
अच्छा
देन वन ऑप्शन इज करेक्ट।
ओके इट इज कास्टेलो नहीं है इट डज नॉट form precipitated when subjected to treatment it is a rotello which is subject to secondary process for resave I think last option fourth one
Yeah, okay. Next is the addition of silicon as an alloying element is useful for cast aluminum alloys because
it improves the fluidity of aluminum melts first option
no, no. One more.
uh, silicon reduce melting last one it reduce the melting temperature of aluminum
Okay. It reduces the solidification shrinkage also.
okay ma'am
Means because the nucleation of silicon particles increases the volume, so the solidification shrinkage is compensated because of the nucleation of silicon particles.
okay ma'am
Next is the when aluminum 7 silicon alloy cooled from 700 degrees Celsius to the room temperature, then its microstructure will contain which features?
only pro-eutectic yes I first option
No, pro-eutectic with the silicon particles will be in the hypo-eutectic silicon alloy. This is sorry, hyper-eutectic. So this is the hypo-eutectic, not hyper. The pro-eutectic silicon particle will be in the hyper-eutectic.
okay
So can you guess the correct option?
primary alpha aluminum and eutectic Si
Yeah, okay. Next question is the phase responsible for low ductility hyper-eutectic aluminum silicon alloy is
primary alpha aluminum
no. Low
yes
ductility.
response
The primary alpha aluminum increases the ductility.
okay silicon eutectic Si
No.
yeah okay. Phase responsible for hyper eutectic primary Si particle only
Yeah, okay. Next question is which of the following statement is correct regarding modification of aluminum silicon alloy by
first
oxidation?
option chemical modifier
Yeah.
hello
Yes, sir.
first option madam chemical modifier deactivate
PPR in the temperature.
yes ma'am
One more. It has one more option correct.
grain refinement it promotes the grain refinement
No, grain refinement does not promote.
uh, I think last option
No,
it prevents the
the modifier
second option
absorb on the surface and prevent the attachment of silicon atoms.
okay ma'am that's
Next question is on cooling of aluminum silicon alloy with higher cooling rate during its solidification.
morphology used to ductility of the alloy decreases
No, in aluminum silicon case,
Okay, ma'am.
Can we end the lecture?
Yes, ma'am. Thank you.